Okay, in this question you are asked to consider the following energy diagram and determine which of the following statements is true. And these statements all have to do with the fact that the equilibrium constant is equal to that ratio of the forward rate constant over the reverse rate constant. And is that greater than or less than 1, okay? So let's think about a couple things that are important before we really decide on an answer. And first of all, let's talk about the activation energy according to this diagram. So we really have two different activation energies here represented. We have the activation energy for the forward reaction, where the reactants become products. They have to get over this energy barrier, so that's for the forward reaction. Okay, but you could also label on here the activation energy for the reverse reaction. In order for these products to go in the opposite direction and form the reactants back, they would have to overcome that energy barrier. So we'll label that the activation energy for the reverse reaction. And as you can see, just clearly from the picture, that the activation energy of that forward reaction is bigger than the activation energy of the reverse reaction. Now the reason why that's important is because if you remember from chapter 13, we learned this equation, the Arrhenius equation, which said that the rate constant is equal to that frequency factor times E raised to the power of the negative EA, so the activation energy, divided by RT. All right? And so the larger the activation energy, the smaller the rate constant. Okay? The larger the activation energy, the larger that energy barrier, the smaller the rate constant. Now if you want to prove that to yourself, you can just plug it into a calculator. Okay, so for example, e to the minus 1 is 0.367, but e to the minus 2, a bigger number, is a smaller result, 0.135. Okay, so if we have a larger activation energy, then that's going to result in a lower rate constant. So what that basically tells us in this case, because the activation energy for the forward reaction is larger than the activation energy for the reverse reaction, that means that the rate constant for the forward reaction is less than the rate constant for the reverse reaction. All right. And why is that important? Well, it goes to something else that we talked about in the beginning of chapter 14, and that is the relationship between these rate constants and the equilibrium constant. Remember that by definition, something is at equilibrium when the rate of the forward reaction is equal to the rate of the reverse reaction. And we could expand that out, okay, because we know how to write rate laws. So the rate of the forward reaction would be the rate constant of the forward reaction times the concentration of that reactant. And at equilibrium, that means that the rate constant times the rate constant of the reverse reaction times the concentration, in this case, of the product. Okay, we just expanded out the rate law. Okay, and now we can collect terms, rearrange and collect terms, and we would find that the rate constant for the forward reaction divided by the rate constant for the reverse reaction. Move all my K's to one side and move the concentration terms to the other side. That would be the concentration of P for product divided by concentration of R for reactant. Okay. Now, what that means is that since we know that this forward reaction rate constant is less than this reverse reaction rate constant, that means that this number is going to be less than 1. Okay, because you're going to have a smaller number divided by a bigger number, so it's going to be less than 1, and that allows us to answer the question. So the answer is going to be that the equilibrium constant is the ratio, the K, the forward reaction, divided by the rate constant of the reverse reaction, and it is less than 1.